Physics lovers and enthusiasts, welcome in this episode about an application of quantum mechanics to crystals. Crystals are well known as expensive gems such as ruby, sapphire and diamond, but those admirable compositions of nature are not restricted to rare and extravagant jewelry. In fact, crystals are the most common way by which materials form in nature. Common examples are ice, salt, transition metals such as silicon and iron, many types of minerals, of course, and even proteins. Crystals are extremely important in science. By using techniques such as X-ray diffraction, scientists are able to figure out the structures of molecules. This is crucial in biology and chemistry since the properties of molecules depend on their three-dimensional shape. This is used, for example, by pharmaceuticals to design drugs and by biologists to understand the functions of proteins. Crystals are also paramount to material science, since their properties such as electrical conductivity, thermal conductivity, heat capacity and optical behaviors can be studied and theoretically predicted. A very good example has been the development of semiconductors on which all modern electronics is based. A crystal is a solid material whose constituents, such as molecules, atoms, or ions, are arranged in a highly ordered manner. More precisely, the atomic nuclei are arranged in a periodic fashion, forming a lattice, which for an ideal crystal would extend to infinity. The lattice is completely specified from its translational vectors R, which are used to pass from one site to any other site. Any vector R can be expressed as a linear combination of primitive vectors, here A1 and A2. The coefficients are integers. Although the nuclei can vibrate, we will assume here that they are static. The nuclei should repel each other since they are positively charged, but we assume that they are held together by some of their electrons, hence forming a lattice of positive ions. Since only a fraction of the electrons are necessary to ensure the cohesion of the lattice, the remaining electrons, which do not contribute appreciably to this bonding, are presumably free to move around from sites to sites. These free electrons are responsible for most of the properties of the crystal. By analogy to molecular chemistry, these latter electrons are denoted as valence electrons, and our goal is to determine the behavior of these electrons. The positive ions exert an electrostatic attractive force on the valence electrons, which we represent by an electrostatic potential V, that should have the periodicity of the lattice. We mathematically write that V of R plus a reciprocal vector big R equals V of R. Perhaps a naive assumption, we will consider the electrons independent and non-interacting with one another, so that we can restrict our analysis to a single electron, while considering that it should be the same for all the other ones. Properties of crystals can only be thoroughly understood by using quantum mechanics. In a nutshell, applying quantum mechanics to crystals means solving Schrödinger equations in a periodic potential. Schrödinger's equation was formulated in 1926, shortly after de Broglie proposed that electrons may be treated as waves. The first method to solve this equation for crystals is known as the plane wave method, formulated by Felix Bloch as early as 1928. It was applied by Hans Bethe the same year to the case of high-energy electron diffraction by crystals. In this episode, I would like to introduce the plane wave method, which I think is foundational in crystal physics. At this stage, a good understanding of quantum mechanics might be necessary. Notions of crystallography can be helpful too, and a good understanding of Fourier transforms will be required. For visualization purposes, we'll be looking at 2D monoatomic crystals. This is relevant since this is the case, for example, for graphene, but also because most of the principles developed here will equally apply to arbitrary 3D crystals. The theory presented here comes directly from the Solid State Physics Bible by Ashcroft and Mermin.